Hello guys, how you doing? I hope everyone is staying safe. I just thought I'd make a video regarding testing some semiconductor parameters on transistors. Basically, recently I've had a chance to buy a couple transistors typically used in audio and all sorts of hobby electronics. The TIP 31C and the TIP 32Cs, basically a complementary pair, 100 volts, 3 amps, and basically they just turned up today. And bought them on eBay. They were very great price. For each one I paid around basically 100 each, and per 100 I paid $16 for each, basically, right? So it was a great opportunity, like a great price to pass on. And the seller is a US seller. Seems to be a reputable seller, right? But the transistors turned up today, and they both showed up. The tip 31Cs, right, and the tip 32Cs. But once I opened up the package, you can't really tell whether a transistor you get, like if they're not obviously like horribly marked or whatever, that you can tell whether they're genuine or not, right? So it's pretty difficult to tell by just looking at the package. So what we'll do today is we'll just test some of the parameters and take a look at the data sheet, right? Take a look at the data sheet and compare some of the measured values with the data sheet, right? So we'll do that. And one thing I've noticed on these transistors is, let's see if this thing could focus on this. Give me a second here. Okay. Seems to be just focusing on the background. These transistors have no marking whatsoever, just completely blank. Yep. So as you can see, they have no marking whatsoever, just completely blank. And if we just zoom in here a bit, it's probably easier to show it like this. You can see both the tip 32Cs and tip 31Cs, they just showed up like this, and no marking whatsoever, right? Just I don't even know who the manufacturer is, right? So what I will do is I will test again, like I said, test the parameters and take a look what we can do. So the first test we'll do is, of course, you could do your simple test using these testers that you get on eBay, right? Just pop it in and let it rip. As you can see, we get I got it from the tip 32C bag, right? And it says that it has an HFE of 68 at 0.63 at 630 microamps, right? And a drop of 563 millivolts. Now the pinouts does match the data sheets on the pinouts for this transistor. Typically it's base, collector, emitter, right? That's what TO220 transistors typically, their typical pinouts is, right? So first test, first pass, it does pass. The gain seems to be on a little bit on the low side, right? But the data sheet does say, so if we scroll down, like I'm looking at the data sheet from On Semiconductors, right? So I don't know again who the manufacturer of these transistors is, but you can see that in the data sheet for the static tests, meaning no dynamic tests, the HFE here, as it's specified, at minus 4 volts VCE and a current of minus 1 amp, basically at IC of 1 amp, the lowest that you can expect at the minimum is 25, right? It says that, right? I would have expected it to be a little higher at lower current. We tested at 630 microns, but again, it seems to have passed that. And you can see the typical performance for the collector current, right, versus the HFE swept from basically I think it's 1 milliamp to, sorry, from a milliamp to about, I would say this is 1 amp, right? 2 amps, 3 amps, goes to about, I think, 4 or 5 amps. But you can see that it does start about 100, right? So that's the typical performance, typical HFE. And just testing it on this tester, that we've gotten a value of about, what is it, 53 or something like that, right? Pretty low, right? You know, just a bit disheartening, I suppose, right? I have here another TIP 32C that I have on my stash from ST Microelectronics. So let's basically let you have a look at this guy. Properly marked, right? You know, with date code and all of that, right? TIP 32C. And I do have the ST Microelectronics data sheet for it. And again, it is basically the same. Like most of the parameters are the same between the two manufacturers. HFE again at 1 amp and VCO 4 volt 25. You know, that's what they specify. And but if we do pop this guy in here and we just test it, you'll see that this guy has quite a bit of gain, right? Of course, it's at 6.1 milliamps and it has a HFE of 164. I would have expected this guy to be like that, right? You know, just again, if we look at the ST Microelectronics data sheet, there is typical characteristics. I don't know if there is one for the, probably not. Yeah. So there isn't one for IC versus HFE characteristics plot, right? So, but it's just, yeah, doesn't instill confidence that these might be genuine ones, right? You know, just, but let's have a look. Let's test a little more. So I will test for HFE in a second, but the first thing I'll test is I will test for the breakdown voltage, the VCO with the base open and collector to emitter directly attached to power supply. The transistor, I'm going to use the ON semiconductor data sheet for this. The maximum is specified for TIP 32C. As you can see, it's 100 volts, right? 100 volts from emitter to collector. And you can see the sustaining, meaning that it can stand that voltage. They give you the test conditions as much as, the test conditions as much as 30 milliamps can pass through that. So it's basically acting like a Zener diode at that, I guess. And for TIP 32C, it's 100 volts. So let's test that. I have here sort of a crude high voltage power supply that I have. And this thing is fed from my Variac, right? So I can vary this. It goes to basically a couple high voltage capacitors right after a rectifier. So I should be able to ramp up this voltage and basically measure the leakage current from emitter to collector and find out when the avalanche breakdown starts. Okay, let me set that up and maybe draw a little bit of schematic to show you what the test will do. Give me a second. Okay, so this is the test setup. Basically the TIP 32C is arranged such that the emitter is directly coupled to the high voltage power supply through a sort of a current limiting resistor, just in case if this thing avalanche is really fast and they just, you know, this gives me time to react, that, you know, just I wouldn't short this high voltage power supply. And I'm gonna put my meter in the microamps range. I'm gonna put my meter in the microamps range and monitor as this transistor breaks down. Basically you could do similar tests for MOSFETs as well, right? You know, to test the VDSS, right? Anyway, so we're gonna do that, and based on the data sheet, the VCO should be greater than or equal to 100 minus 100 volts, where in this case, since the emitters, the VECO with the base open should basically be greater than 100 volts. And they actually tested at ICOs 30 milliamps, right? So I think this is not continuous. I don't think they do that. I think they just pulse it. But just for our case, we can monitor, when about, like, let's say 100, 200 microamps pass through here, this zener is going to convert, this transistor is going to is going to break down, and it just converts itself into a zener, right? So it's going to try to regulate that voltage at whatever the breakdown voltage is of this transistors, right? So it will give us time to react to just back off on the high voltage power supply here. So if you are curious to see how the high voltage power supply is wired, I can show you that real quick here. So basically, I have an auto transformer or a variac directly hooked up to the mains. Actually, it's not directly hooked up to mains. I have an isolation transformer in between here, but I didn't draw it. And it goes to this variac, and I can vary the voltage from 0 to 130 volts AC. And it goes to this transformer here. This transformer has 120 volts on the primary and then 600 volts on the secondary, so I should be able to get quite a bit of high voltage, variable high voltage. And that goes to basically a bridge rectifier and the rectified mains. Well, in this case it's not mains, but anyway, the rectified voltage from this transformer would be smoothed by a couple of capacitors, high voltage capacitors hooked up in series. I think for myself, initially when I was setting this up, I was meaning to use 470 microfarad capacitors, but I'm only using 100 microfarad capacitors. But not to worry, because we're not going to extract a lot of current from here, so the voltage would be substantially smooth out here. So, and the 8.2k current limiting resistor, right? So let's get testing and let's find out what the breakdown voltage of this transistor is. So if you want to quickly take a look at the setup here, there's the input, comes from that transformer, comes through here. The transformer is fed from this guy here, comes from the basically from the auto transformer, and that goes through this wire here, comes through here, basically this mock power supply here that allows me to vary it. And I get variable DC out here because, again, I have an auto transformer here, so I can control the amount of voltage that goes into this transformer, and I get a proportional voltage out here, and I should be able to measure. There's my meter here. Actually, it's not drawn here, but my meter here, another meter, is measuring the voltage here, right? So I can see the breakdown voltage. Okay, let's get testing. Okay, hopefully you can see this. Again, my meter to monitor the collector current as the voltage breaks down, and then this meter to measure the VECO of the breakdown voltage. Okay, let's get going. So I'm gonna turn on my variac. Just if you're curious, my variac is right over here, comes through here. Okay, now let's get going. So let's crank this up. Okay, there you go, the voltage rises. Okay, actually, a little mishap. If you notice there, the current jumped quite a bit, and the voltage was clamped at about, I think, 3 volts or something like that. Yeah, I need to review the footage. But what happened was I actually hooked up this transistor in reverse. Basically, the collector was directly hooked up to the mains. I mean, to the positive power supply. So if we take a look at the schematic real quick, that was a mistake on my part. So basically I had this guy in reverse, right? I had this guy in reverse, and basically it broke down, right? It broke down real quick, right? So basically the collector was directly hooked up to here. The emitter was hooked up to here, right? So yeah, so don't do that. So now I fixed it, so I flipped it, so now we should be able to test the real breakdown voltage. So you can see actually the the capacitors haven't discharged, right? So let's keep going now. So now we're gonna go up. There you go. Now this makes sense. The voltage rises up, so I'm just gonna zoom in now a bit. As you can see, the voltage rises, keeps going up and up. You can see the current, basically the breakdown, the leakage current is extremely low. So I got good confidence that this might be the real tip 32Cs, right? So we go over 100 volts, that's good. So the specification on the data sheet says that it should be greater than 100 volts, and it is. So let's keep going until we get a substantial current on the... Okay, this doesn't make sense. Keeps going. Yeah. Okay, let me check my... Oh, there it goes, right? Starts to break down now, right? I was a bit confused there because... Interesting. So you can see that now. Yeah, you can see there's about... what is that? I mean, you can't see that microamp symbol, right? Because it's actually fading, but... I don't know if you can see it here, right? There we go. So the microamp symbol, there's about 500 microamps of 450 microamps of current, and you can see the transistors broke down, let's say at 175, and it's holding. So now it's acting like a Zener diode, and I could go up, right? There you go. The current increases, but the voltage remains, right? So now it's almost 1.2 milliamps, right? So now if we switch this to milliamp scale, there you go, right? So interesting that this transistor breaks down a lot higher than 100 volts. So I am in my right, I mean, to doubt that these are actually tip 32Cs, right? So we'll test that guy from ST Microelectronics and see if we can compare. Give me a second, let me set that up. Yeah, just want to quickly show you. I turned off my variac. Now you can see the capacitors here. Basically the capacitors here are now discharging, right? The 1 mega ohm, right? This is pretty high resistance for them to discharge, so it does take a bit of time for them to discharge. So I'll just spare you the details, and I'll come back in a second. Okay, so I've set up the ST Microelectronics tip 32C transistor. Basically, as you can see, it's a different package, right? It's still TO220, but it has that specific shaped to ST Microelectronics, where they trim these two ends, right? So I've set it up. Now let's measure the breakdown voltage and the leakage at the same time, right? So let's go ahead, and I'm just gonna power this. Let's keep going. So this guy keeps going. So now we're monitoring obviously the leakage on this side as we crank up the voltage. Keeps going. There we go. Passes at 100 volts. Now let's see where this thing breaks down. Okay, interesting. This guy also goes quite high. There we go. This guy breaks down at 156. And switch this to milliamps. There we go, right? So now we can keep going, cranking up the voltage, but you know, it's the current goes up, but the voltage remains, right? Now it's acting like a Zener diode at that voltage, at the breakdown voltage, right? Okay, interesting observation. Let's keep going. Let's test some other parameter. Okay, next setup that I have is I'm gonna test the basically HFE at a very low collector emitter voltage. Reason is the bipolar junction transistors suffer from what is called the early effect. Basically, as the voltage is increased on VCE here, the current also increases, right? Normally you would expect the transistor collector current should be independent of the VCE voltage, But as the VCE voltage increases, the collector current increases. That's called the early effect. And to minimize that, what's done normally is you test the transistor at a very low voltage, VCE, very low VCE voltage, its current gain, so that you get a very accurate measurement of the HFE, basically, so that it's independent of the collector to emitter voltage. And basically, this is the setup. I'm gonna set this pot. I'm gonna adjust it such that I have 1 amp of current flowing through here, and I'm gonna measure VCE. So basically, this thing will measure VCE. This thing will measure collector current, and this thing will measure base current. So basically, collector current divided by base current gives me HFE. And I'm going to do it at 1 amp. The reason is, in the data sheet, the test conditions for HFE for one of the test conditions is, you can see here, VCE minus 4 volts, they say, right? I'm using it minus 2 volts, right? Because basically, yeah, I'm doing it lower so that I again avoid the early effect. The minimum I should expect is 25, and I'm pretty sure it's gonna pass that. So anyway, let's test it. So basically, my power supply is set up to provide basically 2 volts, and it's limited to 1.25 amps. And basically, it's connected to here. And let's go. Yeah, and the other thing is, one thing I'd like to mention is I put a heatsink on it. Reason is, the test, normally this test is done using a pulse, right? So you can see here, so that temperature doesn't affect the measurements, because also HFE could also be dependent on temperature. So you can see that they specify here on the bottom here that this is done at a pulse test. Pulse width is only less than 300 microseconds, and the duty cycle is 2%. What that means is you have a very long off time, and then they just pulse it, and they basically measure the HFE. You can do that using oscilloscope. Basically, you can capture by measuring the voltages across maybe like this resistor here, right? You could put a current sense resistor here, and you could do it, right? And I'm not doing it since I'm putting it with a high heat sink, and I'm gonna quickly do this test. Hopefully temperature wouldn't be a big issue. Okay, let's do this. So I'll just enable my power supply. Yeah, you can see now there's about 362 milliamps of current flowing through the collector. We can quickly test the HFE. You could do the HFE 363 divided by 6.95. I don't know how much that is. Let's see if I can grab my calculator real quick here. Let's do this. 364 divided by 6.96. You can see that we have an HFE of 52.3, right? So at this current and the base drive, and also VCE very low, right? Only about 2 volts. We're getting about 52 or 53, right? So let's keep going. Now I'm gonna adjust this potentiometer, basically, which is this guy here, until I get 1 amp on the collector current. So let's see if I could put everything in one shot. Let's keep going now. Should lower it. So let's keep going. And let's see if we can see the collector to emitter voltage as well. Okay, let's keep going. I have 10 turn pot here, so okay, let's keep going. Just want to do this precisely at 1 amp. Okay, so let's take a screenshot of this and let's do this measurement. So that's 1 amp at 22.84 milliamps, right? So 1 amp. Now let's do this calculation real quick. 1 amp at 22.84 milliamps. We get 43. We get 44. An HFE of 44. Again, You can see that the transistor hasn't saturated, right? It's still in the active region because VCE is still substantial. And yeah, so it is about 25. So again, very low spec part, right? You know, just quite a bit of low HFE, right? But again, it does pass, right? It meets the minimum requirement in the data sheet. Okay, I'm gonna set up one test, which is basically the collector emitter saturation voltage. Basically, I will draw this and I'll show you how I can test this real quick. Give me a second. Okay, so I've rewired the test to include the test for the VCE SAT, basically the emitter to collector or collector to emitter saturation voltage. And again, if we look at the spec sheet, the collector emitter saturation voltage basically at okay, basically at those specs, I'm actually did set it up for basically what I've done is I didn't set it up for 3 amps. I have actually, like for collector current, I've set it for 375 milliamps collector current, and then divide that by 10 for the base current, right? So basically the base current is set up for 37 milliamps, and the collector current is 375 milliamps, right? So those basically that's what I'm going to be testing it at. And just give me a second, I'll show you a curve where we can get the typical emitter saturation voltage. There's the 5 ohms, it's just a 100 watt resistor, and there's the setup. This one will measure the VCE SAT, will measure the collector current and the base current. Now there is a curve they provide here for typical values for the, if we zoom in a bit here and just pan, there's the curve here, the basically collector emitter saturation voltage. Even they give you the VBE SAT as well, right? You know what you expect. So now we're going to be testing it at collector current of 375 milliamps. So this is in milliamps, this is 10, this is 100, this is 200, 300, 400. So it's going to be somewhere around here. So somewhere around here, and that comes out to be, just looking this from the camera, it should be below 100 millivolts. That's all I need to know, right? It should be below 100 millivolts. This is in millivolts. So it should be below 100 millivolts for the current, the base current and the collector current we're testing it. And we should be able to, I'm not going to check the VBE SAT, right? No, so for that same one, this is 100, 200, 300, 400, so somewhere around here. So we expect a VBE SAT of about less than a volt, right? So what is that? You know, just 900, 800, I don't know, 800 millivolts or something like that. And that's what I took, right? You can see here, that's what I set it up here. So I get the base emitter drop is about 0.8 something. That's how I calculated this values of the resistor here, the base resistor. Okay, let's do this. So let's turn it on, see what happens. Okay, maybe something's not connected because I'm just measuring the power supply voltage. Give me a second, let me troubleshoot and get back to you. Okay, you probably noticed that this meter wasn't connected to the current jack, it was on the voltage jack here. So this is a high impedance input, that's why basically the base was open. That's why the reason. But anyway, so now I've connected it correctly. So let's turn it on again. Okay, there you go. Now you can see that collector current is 352 milliamps. Base current is almost a tenth of that, the base current, and the saturation voltage is 98.7 millivolts. So we expect it to be less than 100 millivolts again, right? So if we go back to this, 100, 200, 300, right? 400, somewhere around here, right? That's where we're measuring right here. and that comes out to be around here. So it is less than 100 millivolts, right? So okay, again, it doesn't match the spec, right? So we might have a genuine part in our hands here. So let me measure the uh, base to emitter saturation voltage while we're at it. So let's see what we get. Just give me a second here. Just setting it up my meter here. I'm going to be using this meter here. So let me set that up and give me a second here. Okay, so as you can see, I'm measuring it right on the base to emitter voltage. And what do we get? We get 0.8. So bang on, like still meeting the spec. By the way, I did this was a bit clumsy here because we are operating in the saturated region of the transistor, and it's not going to heat up, right? You know, just basically the voltage drop is low, so this multiplied by this gives us the power dissipation in the transistor. It's pretty low, so I just grabbed one from the bag here and then just put it here, so I'm not using this. Last test I will do is power. Basically, this device is rated to carry let's go back here to the max values. This device is rated to carry at case temperature of 25 degrees. It can carry 40 watts, right? So again, this test is normally done using a pulse, right? You know, like with a low duty cycle, so that you know you don't heat up the transistor. You know, to keep the case temperature and the junction temperature within operating limits. But for myself, I will temporarily load it, right? You know, just I'll sacrifice. If it dies, it dies, right? I'm gonna sacrifice one. I'm gonna try to load it until 40 watts and basically see if it can survive it. Now, when you do that test, you better make sure that you observe the safe operating limit of the transistor. So let's take a look here. The safe operating limit of the transistor is shown here for tip 32C. I'll try to operate it at a low voltage. So what I will do is because this device can only handle 3 amps maximum, so to get 40 watts I will inject 20 volts and I'm gonna put 2 amps, right? So you can see, right, 20 volts VCE, it's right here, right here, 20 volts VCE. You can go up here and go to 2 amps collector current. That is within the safe limit, right? Now it does say here that this is the limit where you could operate this continuously. It says DC, right? It's not for a pulse operation. So let me set up that test and I'll try to load this guy to 40 watts and see if it doesn't die. So if it doesn't die, we're gonna call it genuine part. Yeah. Okay, give me a second to set up that test. Okay, the last test is set up. Basically, again, like I mentioned, I'm going to be applying 20 volts here, and I'm going to measure the current at 2 amps. 2 times 20 is 40 watts. That's how much this transistor will dissipate. And now, in order to limit the base current, in order it sinks 2 amps, we measured the HFE of this transistor. It was about 443, in that realm when it was thinking about 1 amp. So I use that. So 47 milliamps goes through the base, and basically RB you can calculate using the drop across this guy being 0.7. This formula, using that, you get 415. So I set the spot to 415 ohms, and I can adjust it just so I sink 2 amps here, and that I drop 20 volts here. My power supply is also set. Again, this will measure VCE, this will measure IC, this will measure the base current. So let's go. Again, now I substituted the transistor with the guy that has the heat sink. This test should be as quick as possible. Like I said, normally this test is done using pulse operation, and you can do that using oscilloscope. You can pulse it so that temperature is not an issue, right? So, but this heat sink should be good enough for it for a few minutes of testing. And normally I would put a thermocouple here just to measure the case temperature. so that if it approaches around like say 80-90 degrees, I can just stop the test. But we'll do this real quick. Okay, let's go power it on. There you go. It's actually current limiting. We're sinking more than 2 amps, so I'm gonna increase this resistance to lower the current. So yeah, I think I might not have. So let's take a shot of this. Basically 2 amps at 16.81 volts, right? So 2 amps, we'll calculate the power dissipation. 2.124 multiplied by 16.7, right? Okay, I'll stop my power supply. So if we do that calculation real quick, the power dissipation, now I know it's not really 40 watts, but it's close, so let's do that. The transistor did withstand that for quite a bit, so 2.124, you can see that was 35 watts, right? We loaded it to 35 watts and the transistor didn't die on us, right? So seems a genuine part. What I will do is I'll actually basically increase my the reason why I think there's quite a bit of drop across this like this wasn't quite 16, right? I think that sorry, my bad, it was the power supply limit, the current limit on the power supply is the issue. So I will increase this to say 3 amps and then let's test this again. So let's hit it again. Let's see. Oh yeah, it's quite warm. It is warm, so I'll give it a bit of time to cool off and then we'll hit it. Okay, the heatsink is substantially cooled off, and basically and I've increased the current limit on the power supply, so it shouldn't limit us so that it drops the voltage on the VC. We don't want that. We want to go all the way to 40 watts, even more if we can, just to test this guy. So I'll do this for 10 seconds, and if it survives, then we're gonna call it a good part, because this heatsink is small enough, it's not gonna be able to cool down the junction appropriately. So normally I would throw in a big heatsink for it when I'm doing this test, but just for this time I haven't. So let's keep going. Okay, now watch again the current, IC and VCE. So I'll put them on the same shot. Okay, let's go. So you can see that IC is 20 volts and IC is 2.3 amps. So I'm going to record that. 20 multiplied by 2.33. Okay. And I'm going to count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. Not bad. Still can touch the heatsink. Alright, this transistor is surviving. Okay, keep going. Oh yeah, we are above the safe limit, actually, safe operating area limit. So yeah, okay, I'll turn it off here. And we'll do the calculation. So it looks like the transistor survived. Let's turn it on just to take a look that it didn't die when I turned it off. There we go, still alive. Okay, seems we have a genuine part on our hand. Okay, so now let's do this calculation real quick. 20 multiplied by 2.33. You can see that I've loaded it all the way to 46 watts and it did survive. Yeah, there is few other tests you can do. Basically, you could try to measure the static capacitances across the junctions, and those are not typically accurate measurements, but you could do that. And those capacitances, collector to base, base to emitter, and those capacitance are not given on this. Typically on the other transistor data sheets there are those, right? But they're not given, so I can't test for them. Again, like I said, you could do those static tests, but normally they don't come out accurate. You can also try to do FT test. Maybe I'll make a video on how to do this test. If you have a fast scope and a signal generator that could do maybe a few hundred megahertz, which I have, we'll maybe set up one time to do FT test in a couple transistors and see if we can do that. I will try to set that up. Yeah, but basically, we can say that the tip 32Cs are, the unmarked ones that I got. Again, just get random ones from there. You can see that, they don't have any marking whatsoever, right? Just, right, let's just do this. Hopefully it focuses on it. Yep, you can see no marking whatsoever. So that's why I thought maybe these are not genuine. So I'd done few tests on them, mostly static tests, and they passed. So I'm gonna call these guns genuine. All right, talk to you later. Hopefully next video that I make will be regarding the power amplifier, and we can go from there. Take care, stay safe, bye.